It began with an accident. A physicist sitting in front of a computer screen in 2007, sifting through years of old radio telescope data, not looking for anything in particular, just doing the unglamorous, invisible work of science that nobody films and nobody talks about. And then, buried in an archive of data that had been sitting untouched for 6 years, she found something that should not have been there. A burst. A single, blindingly bright flash of radio waves, so short it was over in 5 milliseconds, so powerful it outshone entire galaxies, and it had come from somewhere so far away that the light, the signal, had been travelling through the universe for hundreds of millions of years before it slammed into a radio telescope in the Australian outback and set off what would become one of the greatest mysteries in modern astrophysics. Nobody knew what it was. Nobody had ever seen anything like it before. And for a while, for a painfully long while, most scientists didn't believe it was real. This is the story of fast radio bursts, and I want to be very honest with you up front. We still don't fully understand them. The mystery is not solved. But what we do know is stranger, more violent and more magnificent than almost anything else we've discovered in the cosmos. These signals travel billions of light years. They release more energy in a single millisecond than our sun does in 3 days. Some of them repeat, some of them seem to pulse with an almost clock-like rhythm. Some of them do things that our best theories cannot yet explain, and the deeper scientists dig, the stranger it gets. So let's start at the beginning. Chapter 1. The Lorimer Burst. A discovery nobody was looking for. The year is 2007. Duncan Lorimer is an astrophysicist at West Virginia University, and he hands a summer student named David Narkovich a hard drive full of archival radio telescope data, and says, essentially, go look through this and see if you find anything interesting. It is the kind of project you give to a student when you don't expect them to find anything. A training exercise, a way to learn the tools. The data came from the Parkes Observatory in New South Wales, Australia, a giant 64-metre radio dish sitting in a paddock in the middle of nowhere, which had been scanning the sky for pulsars. Pulsars are rotating neutron stars that beam radio waves like a lighthouse, and they're well understood, well catalogued, and, if we're being completely honest, not all that surprising anymore. The Parkes telescope had been doing this kind of survey work for years. The data Narkovich was given had been collected in 2001, 6 years earlier, and nobody had looked at it carefully since. And then Narkovich found something, a single pulse, a radio signal that lasted about 5 milliseconds, 5/1000ths of a second. It appeared in just one part of the sky. It was extraordinarily bright, far brighter than any pulsar they had ever catalogued, and it had something unusual in its structure, a property called dispersion. Here's what dispersion means, and why it matters so much. When radio waves travel through space, they don't travel through nothing. Space is not truly empty. It's filled with a diffuse thin plasma, a fog of free electrons spread so thinly that you'd never notice it if you were travelling through it, but there's so much of it across such enormous distances that it adds up. And this plasma does something interesting to radio waves. It slows them down. But it doesn't slow all radio waves equally. Lower frequency radio waves get slowed more than higher frequency ones. So if a signal contains a range of frequencies, which most natural radio bursts do, the high frequency part of the signal arrives at your telescope first, and the low frequency part arrives a little later. This spreading out of the signal in time, from high frequency to low frequency, is called dispersion, and the amount of dispersion tells you roughly how much plasma the signal has passed through, which tells you roughly how far it has travelled. When Lorimer and Narkovich measured the dispersion of this burst, they got a number that made them stop. The signal's dispersion measure was so high, about 375 units, that it implied the signal had travelled through vastly more plasma than our own galaxy could account for. In fact, it implied that the source was not inside the Milky Way at all. It was outside, extragalactic, possibly billions of light years away. Let that sink in. A signal from beyond our galaxy, from somewhere so remote that the light had been travelling since before our solar system existed, had arrived at a radio dish in Australia, lasted 5 milliseconds, and then disappeared forever. Lorimer and his colleagues published the discovery in the journal Science in 2007. The signal became known as the Lorimer Burst, It was, at that point, a singular event. One burst, no repetition, no confirmed counterpart, no source identified, and because it was a single event, and because the data was old and the telescope wasn't the most sophisticated instrument in the world, and because the universe had never done anything quite like this before, a significant portion of the scientific community looked at the Lorimer burst and said, "We don't believe you." Not that Lorimer was lying, but maybe there had been some kind of instrumental artifact, a glitch in the electronics, terrestrial radio interference, a microwave oven, a mobile phone, a passing satellite. The history of radio astronomy is littered with signals that turned out to be mundane human technology bouncing off the ionosphere or leaking into a receiver. There was even a famous case at Parkes years later, where astronomers tracked down a mysterious repeating signal and found it was coming from a microwave oven in the observatory's own kitchen. Nobody was accusing Lorimer of making things up, but extraordinary claims require extraordinary evidence, and one burst, 6 years old, from a single telescope was not yet extraordinary evidence. So the field waited and waited. And then, in 2013, everything changed. A team led by Dan Thornton reanalyzed newer data from the Parkes telescope and found not one but 4 more bursts. 4 independent events, each in different parts of the sky, each with high dispersion measures indicating extragalactic origin, each lasting just milliseconds. They were all different. They came from different directions. They had different brightness levels, different structures, but they all shared the same essential fingerprint: brief, blindingly powerful, and from incomprehensible distances. The Lorimer burst was no longer alone. A new class of astronomical phenomena had been born. They were named fast radio bursts, FRBs, and suddenly, the entire field of radio astronomy became very interested. Chapter 2. What exactly is a fast radio burst? Let's slow down and make sure we understand what we're actually talking about, because the numbers involved in FRBs are the kind of numbers that the human brain is genuinely not designed to process intuitively. You have to work at it. You have to sit with them. A typical fast radio burst lasts between a fraction of a millisecond and a few milliseconds. The shortest confirmed bursts are around 30 microseconds, 30 millionths of a second. The longest are maybe 20 milliseconds. So we are talking about events that are in many cases shorter than the blink of an eye by a factor of hundreds. In that fraction of a second, these bursts release an absolutely staggering amount of energy. We're talking about energies on the order of 10 to the power of 38 joules, sometimes more. To put that in some kind of perspective, our Sun, which is a perfectly respectable middle-aged star, puts out about 3.8 times 10 to the power of 26 joules of energy per second. A fast radio burst can release more energy in a single millisecond than our Sun emits in 3 days. Some of the more energetic ones release as much as our Sun would output over decades, all in less time than it takes you to snap your fingers. And this energy is released in the form of radio waves specifically. Not visible light, not X-rays, not gamma rays, radio waves, which is itself a strange and important detail that any good theory about FRBs needs to explain. Now, the most important property of FRBs, the one that tells us where they come from, is that dispersion measure we talked about earlier. By 2023, astronomers had catalogued hundreds of FRBs, and the vast majority of them had dispersion measures that placed their origin well outside our galaxy. Not just a little bit outside, billions of light years away. The most distant confirmed FRB source, at the time of this writing, is thought to be around 8 billion light-years from Earth. 8 billion light-years. The universe itself is only about 13.8 billion years old. That signal began its journey when the universe was less than half its current age. This distance has enormous implications for how bright these things actually are. When you detect a signal from a billion light-years away, and it still arrives at your telescope as a clearly identifiable burst, that means the original explosion of radio energy must have been almost incomprehensibly powerful. If a fast radio burst went off inside our own galaxy, say a few thousand light-years away, which is nothing by cosmic standards, it would be bright enough to potentially affect electronics on Earth's surface. There is one FRB that we know of that did come from inside our galaxy, and we'll get to that. It is one of the most important events in FRB history. But first, the structure. When astronomers plot out the signal from a fast radio burst, it's not just a uniform blob of radio waves, it has structure. Some FRBs show multiple subpulses, little bursts within the burst separated by fractions of a millisecond. Some show drift patterns, where successive subpulses shift to slightly lower or higher frequencies. Some are incredibly narrow in bandwidth, others are broad. Some are highly polarized, meaning the radio waves are all oscillating in preferred direction, which tells you something about the environment through which the waves passed, and about the mechanism that created them. The fact that FRBs have this kind of detailed structure is actually good news for scientists because structure means information. Every feature of that millisecond-long signal is a data point. The dispersion tells you about the electron density between us and the source. The polarization tells you about magnetic fields. The subpulse structure tells you about what's happening at the source itself. The bandwidth tells you about the emission mechanism. FRBs are brief, but they are information-rich. Now, here is the question that every single person who learns about FRBs asks immediately. Are they all the same thing? Do they all come from the same type of event, the same type of object? Honestly, we don't know. And this is where things get genuinely complicated because as more FRBs were discovered, a startling split emerged in the population. Some FRBs are one-off events. They happen once in a particular patch of sky and never happen again, at least not in any time frame we've observed. We call these non-repeating FRBs, though it's worth noting that the absence of a repeated detection doesn't mean the source never repeats. It might repeat very rarely, or it might repeat at frequencies or times we weren't watching, but then there are the repeaters. Some FRBs go off again and again and again from the same location in the sky, not with perfect regularity, but repeatedly, unpredictably, sometimes pouring out dozens of bursts in a single hour, and then going quiet for weeks or months. These repeating FRBs opened up an entirely new dimension of the mystery. If an FRB is a one-off event, a star exploding, two neutron stars colliding, you'd never expect it to repeat. But some of them do repeat, which means the source is surviving, which means it's a different kind of object, or a different kind of process. Or maybe there are multiple types of FRBs from multiple types of sources. Maybe what we call fast radio bursts is actually several different phenomena that happen to look similar when detected from billions of light years away. This is not a comfortable idea for scientists who like clean, unified theories, but it is a real possibility that the field takes seriously. The repeaters versus non-repeaters debate is, as of today, one of the central unresolved questions in FRB science, and it's been going on since a particular source was discovered that would change everything about how we thought about these events. Chapter 3, FRB121102, the repeater that rewrote the rules. In November 2012, the Arecibo telescope in Puerto Rico, at that time the world's largest single-dish radio telescope, detected a fast radio burst. It was catalogued with the designation FRB121102, based on the date of its detection, the 2nd of November 2012. It seemed like just another burst, one more data point in a growing catalogue. Then in 2015, astronomers pointed Arecibo back at the same region of sky and detected another burst from the same location, then another. FRB121102 was repeating. This was the first confirmed repeating FRB ever discovered, and it created a sensation in the astronomy community. Because now, instead of having to wait for a one-off event and desperately scramble to follow up before it faded away, astronomers could actually plan observations. They could point telescopes at a known location and wait for it to go off again. They could study it in detail. They could use different telescopes simultaneously to capture the event at different wavelengths, in different ways, and what they found when they did this was extraordinary. First, the location. By carefully triangulating the positions of multiple bursts from FRB 121102, astronomers were able to pinpoint the source to a specific galaxy about 3 billion light-years away. Not just any galaxy, but a small, faint, irregular dwarf galaxy. The kind of galaxy that's dim and metal-poor and chaotic, very different from the large, well-organised spiral galaxy that our Milky Way is. And within that galaxy, the source appeared to be associated with a compact, persistent radio source. Something that was glowing faintly in radio waves all the time, even between bursts. That persistent source was itself a mystery. Was it a remnant? A surrounding nebula? Something else entirely? It seemed to sit in an environment with an extremely strong and complex magnetic field, based on the polarization properties of the bursts. Second, the sheer volume of bursts. When astronomers watched FRB 121102 carefully with Arecibo, they detected bursts arriving at extraordinary rates during active periods. In one 2016 campaign, they detected over a dozen bursts in a single session. Subsequent campaigns detected hundreds. By 2021, a Chinese radio telescope had detected over 1,600 bursts from FRB 121102 in a single 47-day observation period, including a window in which 122 bursts arrived in a single hour. Over 1,000 bursts from a single source, each one of them releasing more energy than our Sun puts out in days, all coming from a 0.3 billion light-years away, where something, we still don't know exactly what, is doing this over and over again. Third, the structure of the bursts from 121102 revealed something that nobody expected. The bursts appeared to cluster in frequency. Each burst occupied a particular range of radio frequencies, and the center of that range drifted, systematically, not randomly, from burst to burst. Some researchers interpreted this as evidence of a specific emission mechanism, something about the way energy is being converted into radio waves at the source. Others saw it as a signature of the environment immediately around the source. Either way, it was information, data, constraints on the theories, and the theories were proliferating. By the time FRB 121102 had been confirmed as a repeater, the list of proposed explanations for FRBs included magnetars, highly magnetized neutron stars, rotating neutron stars similar to pulsars, collisions between neutron stars, supernova, cosmic strings, black hole evaporation, interactions between neutron stars and their companion stars, alien signals. Yes, that one showed up in the peer-reviewed literature from a serious research group at Harvard, though it was quickly walked back, and more. The alien hypothesis deserves a brief moment here, because I know you're thinking about it, and because the scientists who proposed it were not cranks. They ran the numbers and asked whether a lighthouse-type beam of focused radio energy, designed to propel a light sail spacecraft, could produce something that looked like an FRB. The answer, mathematically, was yes. The numbers were not obviously absurd, but the hypothesis failed the test of being the simplest explanation, and it was not widely adopted. Still, it says something about how weird fast radio bursts are that a serious Harvard astrophysics paper considered aliens as a possibility without being immediately laughed out of the field. The magnetar hypothesis, though, was from the beginning the leading candidate. Let me explain why, and what a magnetar actually is, because this takes us into some of the most extreme physics in the known universe. Chapter 4. Magnetars, the most violent objects in the universe. To understand magnetars, you need to understand neutron stars, and to understand neutron stars you need to start with stellar death. When a star much more massive than our Sun, say 8 to 20 times more, massive, runs out of nuclear fuel, it can no longer support its own weight against gravity. The core collapses in a fraction of a second. The outer layers bounce off the core and explode outward in what we call a supernova, one of the most energetic events in the universe. But the core itself doesn't disappear. It collapses down to an object perhaps 20 kilometers across, about the size of a city, but packed with more mass than our entire Sun. At those densities, protons and electrons are forced together to form neutrons. The result is a neutron star, an object so dense that a teaspoon of its material would weigh roughly 1 billion tons on Earth. Gravity on the surface of a neutron star is about 2 billion times stronger than Earth's gravity. The escape velocity, the speed you'd need to break free from its surface, is about half the speed of light. Neutron stars are already the most extreme objects we know of in the universe that aren't black holes, but some neutron stars are even more extreme than others. A magnetar is a neutron star with a magnetic field so powerful that it defies everyday language. A typical refrigerator magnet has a magnetic field of about 0.01 Tesla. Earth's magnetic field is about 0.00005 Tesla. The strongest magnetic fields we can create in a laboratory for more than a tiny fraction of a second are around 45 Tesla. The magnetic field of a typical neutron star is around 100 million Tesla. The magnetic field of a magnetar is somewhere between 10 to the power of 10 and 10 to the power of 11 Tesla. 100 billion Tesla. To give you a sense of what that means, at that field strength, quantum effects kick in that don't exist under any other conditions in the universe. The atoms in your body, if you somehow existed in the vicinity of a magnetar, would be stretched into thin cylinders along the magnetic field lines, because the magnetic forces on the electrons would overwhelm the electric forces holding atoms together. We're talking about physics that cannot be replicated anywhere on Earth. Physics that only exists in 1 or 2 places in the known universe that we've found. There are roughly 30 known magnetars in our galaxy. They are identified by their sporadic outbursts. Bursts of X-rays and gamma rays, sometimes catastrophic giant flares that light up the entire sky. The most famous magnetar outburst ever detected was on December 27, 2004, when a magnetar called SGR 1806-20 released a giant flare that, despite being 50,000 light-years away, well within our own galaxy, was so bright in gamma rays that it partially ionized Earth's upper atmosphere. It briefly compressed Earth's magnetosphere from 50,000 light-years. The total energy released in that 1/10 of a second flare was more than our Sun releases in 250,000 years. Now you start to see why magnetars were the first obvious candidate for FRB production. If a giant flare from a magnetar 50,000 light-years away can affect Earth's atmosphere, what would a similar flare look like from a different galaxy, billions of light-years away? At that distance, the gamma-ray flare would be undetectable, too dim to see. But if the event also produced an intense burst of radio waves, which some theorists predicted it should, and if the radio emission was beamed, focused in a particular direction by the magnetar's powerful magnetic field, then from billions of light-years away, you might detect exactly what we detect: a brief, blindingly bright radio flash. The magnetar model has a lot going for it. Magnetars exist. They produce outbursts. They can produce repeated outbursts, because the star itself survives. It just releases energy stored in its magnetic field. They live in environments with powerful magnetic fields. They can form in dwarf galaxies, where star formation rates are high, and massive star deaths, which produce the neutron stars that become magnetars, are common. Almost everything about the magnetar picture fits at least some of what we see in FRBs. But here's the thing: fits some of what we see is not the same as explains everything. And as the FRB catalogue grew, the data started throwing up challenges to even the magnetar model. Some FRBs seemed to come from environments that were very different from what you'd expect around a young magnetar. Some had properties that were hard to explain with standard magnetar physics. Some non-repeating FRBs seemed to come from old elliptical galaxies, where star formation has essentially stopped, which means very few new neutron stars are being born, which means magnetars should be rare. If magnetars make FRBs, why are FRBs occurring in places where magnetars should barely exist? These were not fatal objections. Scientists came up with workarounds. Maybe some FRBs come from old neutron stars that were spun up again by accreting matter from a companion star. Maybe some come from the mergers of neutron stars, which can form a magnetar briefly before collapsing into a black hole. Maybe the population of FRBs is genuinely diverse in origin, but the field needed more than theory. It needed a smoking gun, and in April 2020, it got one. Chapter 5: The Galactic FRB. Proof from our own backyard. April 28, 2020. Radio astronomers around the world are alerted by an automated system. A fast radio burst has been detected coming from inside the Milky Way, from a known magnetar no less. SGR 1935 +2154, located about 30,000 light-years from Earth, has just produced what appears to be the first FRB ever detected from within our own galaxy. The CHIME telescope in Canada detects it. The STARE 2 telescope in the United States detects it. Both see the same event. It is a burst of radio waves lasting about a millisecond, with a brightness and energy profile that, had it occurred at the distances where most FRBs originate, would have been perfectly consistent with a typical extragalactic fast radio burst. This is the moment that the magnetar hypothesis stops being a hypothesis and starts being a near certainty for at least some FRBs. Here is a magnetar, here is a fast radio burst. The magnetar made the fast radio burst. Case closed for at least one population of FRBs. But wait, let's be careful here, because the event also revealed something complicated. The burst from SGR 1935 +2154 was incredibly bright by the standards of any radio emission from a magnetar, but it was actually much weaker than the most energetic extragalactic FRBs we've observed, by a factor of around 1,000 to 10,000. So this magnetar produced something that looked like an FRB, but a much fainter version of the brightest FRBs we detect from billions of light-years away. This either means that magnetars can produce a wide range of burst energies, and we're just seeing the weaker end from SGR 1935 +2154, or it means that the most powerful extragalactic FRBs have a different origin, or at least a different physical mechanism, than this galactic event. Most astronomers lean toward the first interpretation. Magnetars can produce bursts across a huge range of energies, and SGR 1935 +2154 just gave us a relatively modest one. The brightest extragalactic FRBs might be exceptional magnetar flares, perhaps involving some kind of resonance or specific geometric alignment or magnetic field configuration that produces an unusually powerful radio burst. But the uncertainty is still there. Science is honest about that. What the 2020 detection did, beyond confirming the magnetar link, was something even more practically valuable. It triggered a worldwide campaign of observations of SGR 1935 +2154. Teams of astronomers pointed every telescope they had at this magnetar, X-ray, gamma-ray, optical, radio, to try to catch every wavelength of its activity simultaneously, and they found something fascinating. The big radio burst on April 28th was accompanied by an X-ray burst from the magnetar. The radio and X-ray emission were closely correlated in time, separated by just a small fraction of a second. This timing told theorists something crucial about where in the magnetar's environment the radio emission was being produced and what physical process was generating it. The details are complex and still debated, but the basic picture that emerged was one in which the magnetar's extreme magnetic field was somehow converting stored magnetic energy into a coherent beam of radio waves, possibly involving some kind of magnetic reconnection event. The same basic process that drives solar flares on our much gentler sun, but scaled up by factors of billions. This wasn't the end of the story. In fact, in many ways it was the beginning of a new chapter. Because just when the FRB community was starting to feel like maybe finally they understood what they were dealing with, the universe threw them a curveball. Actually, it threw them several. Chapter 6. The periodic FRB. When the universe starts keeping time. In 2020, the CHIME collaboration, the Canadian Hydrogen Intensity Mapping Experiment, which had rapidly become the world's most productive FRB detecting instrument, announced something strange about a repeating FRB they had been monitoring. The source, called FRB 180916, wasn't just repeating, it was repeating on a schedule. Specifically, bursts from FRB 180916 arrived in clusters during a roughly 4-day active window, followed by about 12 days of silence. Then another 4-day active window, then 12 days of silence, over and over with an overall period of about 16 days. This was unmistakably periodic behaviour. The universe was keeping time. Why would an FRB go off in regular cycles? A few explanations immediately jumped to mind. One possibility, orbital motion. If the FRB source, say a magnetar, is in a binary system with a companion star, its orbit around that companion would create a regular period. As the magnetar orbits, it sometimes faces toward Earth and sometimes away. Or the companion star might periodically sweep material toward the magnetar, triggering bursts. Or the companion might periodically obscure our line of sight, blocking the bursts during part of the orbit and letting them through during another part. A 16-day period would correspond to a particular orbital separation and stellar configuration, and while it would be an unusual binary system, it wouldn't be an impossible one. Another possibility: free precession. Just as Earth wobbles on its axis over thousands of years, a neutron star can wobble on a timescale that depends on its internal structure. If the magnetar's emission beam precesses, sweeps around like a lighthouse, it would periodically sweep through our line of sight and then away from it, creating a regular on-off pattern. A third, more exotic possibility: a super long-period pulsar. Normal pulsars spin many times per second, and produce a pulse with each rotation. Could there be a special kind of pulsar or magnetar that rotates with a period of 16 days? Theoretically, very slowly rotating neutron stars can exist, though they're rare, and the emission mechanisms would be different. None of these explanations has been definitively confirmed for FRB 180916, but the existence of periodicity gave theorists a crucial new constraint. Whatever is making these bursts, it has a clock. It has some process that repeats with extraordinary regularity over timescales of days to weeks. That is a powerful clue. Then came an even stranger discovery. Another repeating FRB, called FRB 121102, our old friend, the first known repeater, turned out to also show periodic behaviour, but on a completely different timescale, roughly 157 days, an active window of about 90 days, followed by about 67 days of silence. Over 4 months between active periods, an enormous timescale suggesting a very different kind of system, or a very different mechanism than the 16-day cycle of FRB 180916. 2 repeaters, 2 completely different periods. If both are explained by orbital motion, they represent 2 completely different binary systems. If both are explained by precession, the magnetars have vastly different precession rates. Or perhaps the periods come from entirely different physical mechanisms. The question of whether all periodic FRBs share the same origin, or whether there are multiple ways for an FRB to become periodic, remains open. But here's the thing about periodicity that makes it so valuable to scientists. It gives you something to predict. If you know the period, you can predict when the next active window will be, and you can have every telescope in the world ready and waiting at that exact moment. No scrambling, no luck, no catching a burst by accident. You prepare, you observe, and if your period measurement is correct, the universe obliges. This is exactly what teams around the world started doing, and they started catching FRBs in extraordinary detail, with multiple simultaneous observations across different wavelengths. Each observation campaign added another layer of information. The picture kept getting richer, and the richness kept revealing new complications. We will get to more of those complications in a moment. But first, I want to step back and explain why all of this matters beyond the pure joy of figuring out what mysterious cosmic objects are. Because fast radio bursts are not just fascinating in themselves, they are also potentially the most powerful tool astronomers have ever discovered for understanding the structure of the universe itself, and that is not an exaggeration. Chapter 7: FRBs as Cosmic Probes, Mapping the Invisible Universe. Here is something that doesn't get enough attention in popular science coverage of fast radio bursts, and it is, in some ways, more important than figuring out what makes them. The universe between galaxies is not empty. It contains matter, mostly hydrogen and helium, the leftover stuff from the Big Bang, but this matter is so diffuse and so faint that it's essentially invisible to most of our telescopes. It doesn't shine in visible light. It barely shines in any wavelength. For decades, cosmologists knew it had to be there based on their models of how the universe formed and evolved, but actually finding it observationally was a different matter entirely. This was actually a famous problem in cosmology known as the missing baryon problem. Baryons are ordinary matter, protons and neutrons, the stuff that you, me, planets, stars and galaxies are made of. cosmological models predicted that there should be a certain amount of baryonic matter in the universe. But when astronomers added up all the baryonic matter they could actually observe, stars, gas in galaxies, gas between galaxies that they could detect, they only found about half of what the models predicted. Where was the rest of the ordinary matter? The answer, most theorists believed, was that the missing baryons were hiding in a warm, diffuse intergalactic medium, a cosmic web of gas threads connecting galaxy clusters, too faint to see directly but present throughout the universe. And fast radio bursts, it turns out, are the perfect tool to find this gas. Remember dispersion, the slowing and spreading of radio waves as they travel through plasma. Every electron between the source of an FRB and our telescope contributes to the dispersion measure we observe. This includes electrons in the Milky Way, electrons in the host galaxy of the FRB, and, crucially, electrons in the intergalactic medium between us and the source. If you know how much dispersion comes from the Milky Way, and you know how much comes from the host galaxy, you can subtract those contributions, and what's left represents the contribution from the intergalactic medium. And the intergalactic medium's contribution is related to both its density and the distance to the FRB. If you independently know the distance to the FRB, from a measured redshift for example, then you can use the dispersion measure to estimate the density of intergalactic electrons. This is essentially weighing invisible matter using nothing but a millisecond radio flash. And in 2020, it worked. A team of astronomers used a sample of FRBs with known distances, FRBs that had been localized to specific galaxies with measured redshifts, to measure the density of the intergalactic medium. What they found was that the intergalactic medium contains exactly enough matter to account for the missing baryons. The missing baryon problem, which had perplexed cosmologists for decades, was solved. The matter was there all along, spread throughout the cosmic web between galaxies, invisible but detectable through the lens of fast radio burst dispersion. This was a landmark result, and it demonstrated that FRBs are not just curiosities, they are precision instruments. Every FRB that arrives at our telescopes is a probe that has sampled the material along its entire journey from source to Earth. It carries in its dispersion, its rotation measure, its scattering properties, a detailed record of everything it passed through. Think about what that means for the future, as we detect thousands, eventually hundreds of thousands, of FRBs from sources spread across different distances and different directions. We will be able to build a three-dimensional map of the matter distribution in the universe. We'll be able to trace the cosmic web. We'll be able to measure the magnetic field structure of the universe on the larger scales using the rotation of the polarization angle of FRB signals. We'll be able to test models of cosmic structure formation with a precision that was previously impossible. FRBs, it turns out, might be the most powerful cosmological tools ever discovered, not just because of what makes them, but because of what they can tell us about everything they pass through on their way to us. Chapter 8. The Chime Revolution. Building a machine to catch lightning. For most of the first decade after the Lorimer burst, FRB detection was painfully slow. Years would pass between discoveries. The Parkes telescope found a handful. Arecibo found a handful. The entire global catalogue grew at a rate that made it hard to do serious statistical analysis. You can't draw conclusions about a population from 5 or 10 events. You need hundreds. You need thousands. The problem was the telescopes themselves. Traditional radio dishes are incredibly sensitive, but they have a narrow field of view. To detect an FRB, you need to be pointing your telescope at exactly the right part of the sky, at exactly the right moment. Given that FRBs last milliseconds and can appear anywhere in the sky, the odds of catching one with a traditional dish are terrible, unless you're monitoring a known repeating source. For one-off events, which might represent the majority of FRBs, you are basically waiting for lightning to strike your particular patch of sky. What you really want is a telescope that watches a huge chunk of the sky simultaneously all the time, so that when an FRB goes off anywhere in its field of view, you catch it automatically. This is exactly what the Canadian Hydrogen Intensity Mapping Experiment CHIME was designed to do, though FRBs weren't actually its primary mission. CHIME was originally built to study cosmology, specifically to map the distribution of hydrogen gas in the universe by detecting the 21 centimeter radio emission of hydrogen at different redshifts. But its design made it almost perfectly suited for FRB detection as a side project. CHIME consists of 4 enormous half-pipe-shaped reflectors, each one 100 meters long and 20 meters wide, arranged in parallel like a massive set of ski jump ramps. Rather than steering its reflectors mechanically, CHIME uses digital signal processing to synthesize thousands of beams simultaneously, effectively watching a huge swath of the sky all at once, every second of every day. It can't be pointed, it just stares at whatever passes overhead as Earth rotates. But that turns out to be exactly the right design for catching transient events. When CHIME came online in 2018, the rate of FRB discovery exploded almost overnight. Within the first year, CHIME had detected more FRBs than had been found in the entire previous decade. By 2021, it had published a catalogue of nearly 500 events detected in its first year of full operation, an absolutely transformative contribution to the field. By 2023, CHIME was detecting multiple new FRBs every single day. This flood of data changed everything. Suddenly, astronomers had a real population to work with. They could ask statistical questions that simply couldn't be answered before. How are FRBs distributed across the sky, uniformly or clumped? What is the distribution of their energies? Are repeaters and non-repeaters genuinely different populations? And if so, in what ways? How does the FRB rate change with distance? Are there more of them in the early universe or in the late universe? Some of the answers were expected. FRBs appear to be isotropically distributed, spread uniformly across the sky, with no preference for the plane of the Milky Way or any particular direction, consistent with their origin being extragalactic. The number of detected FRBs increases sharply with decreasing brightness, which means there are far more faint FRBs than bright ones, suggesting a population extending to enormous distances. Other answers were genuinely surprising. The repeaters, when examined carefully, seemed to have different statistical properties from the non-repeaters. They tended to have wider bursts. Each individual burst lasted longer, in milliseconds. They tended to have narrower bandwidths. Their emission was concentrated in a smaller range of radio frequencies. These differences were subtle but statistically significant. They suggested that even if both populations are caused by magnetars, something is different about repeating source magnetars and non-repeating source magnetars. Perhaps their age, perhaps their magnetic field configuration, perhaps the environment they inhabit. But CHIME did more than just rack up detections. It enabled a new generation of FRB follow-up campaigns because now there were so many known sources, especially repeaters, that you could organise dedicated multi-telescope observation campaigns with a reasonable expectation of catching bursts, and those campaigns started producing results that pushed the boundaries of what we thought we knew. One of the most remarkable results came in 2022, when CHIME's outrigger stations, smaller auxiliary telescopes placed at distances of hundreds to thousands of kilometres from the main instrument, achieved a level of localisation precision that had previously been impossible. By comparing the precise arrival time of a burst at each outrigger station, the team was able to pinpoint the position of some FRBs to within arc seconds, precise enough to identify which specific galaxy the burst came from, and even where within that galaxy. The spatial resolution available to these intercontinental baselines is comparable to that of a telescope the size of a continent, and it opens up the possibility of localizing hundreds of FRBs per year to specific host galaxies rather than just rough sky positions. That kind of precise localization is what transforms FRBs from interesting curiosities into precision tools. You need to know where an FRB came from, which galaxy, at what distance, to properly use its dispersion measure as a probe of the intergalactic medium. You need precise positions to identify the host galaxy and study its properties. You need good localizations to figure out where within the host galaxy FRBs tend to occur, in star-forming regions, in galactic centers, in the outskirts. All of these questions are only answerable with good positions, and the answers, as they've started to come in, have been surprising. Chapter 9. Host galaxies, FRBs, are everywhere, and that's a problem. When astronomers first started localizing FRBs to specific host galaxies, the expectation, based on the magnetar model, was relatively clear. Young magnetars form from the deaths of massive stars, which happen in regions of active star formation. So FRBs should prefer young star-forming galaxies. They should tend to occur in the spiral arms of spiral galaxies, or in irregular dwarf galaxies with high star formation rates, places where new stars are being born and dying rapidly, and indeed some FRBs do exactly this. The first precisely localized FRBs tended to come from dwarf galaxies or star-forming regions, which was reassuring for the magnetar model. But then, as more localizations accumulated, the picture got more complicated. FRBs started turning up in old elliptical galaxies, the red dead galaxies where star formation stopped billions of years ago, and where young magnetars should essentially not exist. FRBs turned up in the outskirts of galaxies, far from any star-forming region. FRBs turned up in globular clusters, ancient dense balls of old stars that orbit the main body of some galaxies. These globular cluster FRBs were particularly puzzling. Globular clusters are among the oldest structures in the universe. The stars in them are typically 10 to 13 billion years old. Massive stars, which die quickly and produce neutron stars, burned out in globular clusters billions of years ago. There should be essentially no young magnetars in a globular cluster, yet in 2022 an FRB was localized to a globular cluster in a nearby elliptical galaxy called M81, just 12 million light-years from Earth, one of the closest FRBs ever detected. And in 2023, another repeating FRB was found to originate from a globular cluster, associated with a different elliptical galaxy. What on Earth, or rather, what off Earth, is making FRBs in globular clusters? The leading alternative explanation involves something called a low-mass X-ray binary. In the dense environments of globular clusters, stellar interactions happen far more frequently than in the open disk of a galaxy. Stars can exchange partners or undergo gravitational encounters that modify their orbits. An old neutron star, a pulsar, or an ancient magnetar whose magnetic field has largely decayed, can capture a companion star and start pulling material off it. This accretion can spin the neutron star back up to high rotation speeds, re-energizing it. And some theorists suggest that in certain configurations this kind of accreting neutron star system could produce fast radio bursts. But there's another possibility that's even more exotic: collapsed stellar remnants forming a magnetar through the merger of two white dwarfs or two neutron stars. In the dense environments of globular clusters, such mergers happen at higher rates than elsewhere. If two compact objects spiral together and merge, the product can be a rapidly spinning, highly magnetized neutron star, effectively a brand new magnetar, even in an ancient environment. This would neatly explain how you can have FRBs in old, star formation-free systems. The diversity of FRB host galaxies is, depending on your perspective, either deeply frustrating or deeply exciting. It's frustrating because it means that no single, simple model explains everything. There probably isn't one type of object in one type of environment that accounts for all FRBs. It's exciting because it means FRBs are a more diverse and richer phenomenon than anyone initially thought, potentially involving multiple astrophysical processes, giving astronomers a wider window into extreme physics. What is becoming increasingly clear is that the FRB rate in the universe is staggeringly high. Based on the detections from KIME and other telescopes, astronomers estimate that across the entire observable universe, fast radio bursts occur at a rate of roughly thousands to tens of thousands per day. Some estimates go higher. The universe is absolutely crackling with these events, constantly. Most of them we will never detect because the signals are too faint by the time they reach us, or our telescopes weren't pointing the right way, or the burst happened in a direction obscured by the plane of our own galaxy. But they are happening, all the time, everywhere. Every second of every day, somewhere out there, something is going off with the energy of the sun's output for days or weeks, and it's doing it in a millisecond. The universe is not a quiet place. Chapter 10. The structure problem. What's actually happening at the source? Let's talk about the actual physics of the emission, because one of the strangest things about fast radio bursts is not just that they happen, or where they happen, but how they happen. The mechanism by which any object converts energy into a bright, coherent burst of radio waves is one of the deepest unsolved problems in FRB science. The word coherent is key here. When we say a radio emission is coherent, we mean that the radio waves are being produced in phase with each other, synchronized, like a laser, rather than scattered and random like the light from a light bulb. Coherent emission is far more efficient than incoherent emission. You can produce a much brighter signal from the same amount of energy if the emission is coherent. The brightness of FRBs essentially demands that the emission be coherent. If it were incoherent, like a thermal source, radiating randomly, you would need a physically impossibly small, impossibly hot object to explain the observed brightness. Even for a neutron star, the numbers don't work unless the emission is coherent. But producing coherent radio emission is not simple. It requires a specific kind of plasma physics, the kind of physics that occurs, for example, in the magnetospheres of pulsars, where rotating magnetic fields drive currents of electrons that can produce coherent radio pulses. This is, in fact, one reason why pulsars are a natural starting point for FRB models. We know that rotating neutron stars with strong magnetic fields can produce coherent radio emission, because we see it every time we detect a pulsar. But FRBs are not pulsars. They are orders of magnitude brighter than pulsars. The brightest FRBs are about 10 billion to 100 billion times brighter than the brightest pulsars. Whatever coherent emission mechanism produces them, it is operating at a scale that dwarfs anything we see in normal pulsars. Something is energizing the emission to levels that go far beyond what ordinary pulsar physics can account for. Two broad categories of models have emerged for the emission mechanism. The first category places the emission inside or very close to the magnetaire, within its magnetosphere, the region of space dominated by the star's magnetic field. In these models, a sudden magnetic event, a magnetic reconnection, a quake in the crust of the magnetar, a sudden rearrangement of the magnetic field structure, drives a pulse of particles through the magnetosphere that produces coherent radio emission, somewhat analogously to what pulsars do but at vastly higher energies. The second category places the emission much farther from the magnetar, in a surrounding nebula or in a relativistic outflow, a jet or wind, launched by the magnetar. In these models, the magnetar launches a fast-moving shell of material outward, and when this shell collides with surrounding material, shock waves form, and these shocks accelerate particles that produce coherent radio emission. This is, very roughly, similar to what happens when a star produces a gamma-ray burst, but the radio emission in FRBs requires specific conditions in the shock that are quite hard to arrange. Both categories of model have detailed, sophisticated versions that have been worked out mathematically, and both face challenges when confronted with the data. The magnetospheric models struggle to explain the full range of FRB energies and time structures, particularly the complex multi-component bursts seen in active repeaters. The shock models face challenges from the very short timescales of FRBs, milliseconds, which place tight constraints on how small and compact the emission region must be, something that's hard to achieve in a diffuse outflow. The two most active theoretical camps, magnetospheric and shock, have been arguing about this for years, and the debate continues. What's needed, as always, is better data. Specifically, what's needed is simultaneous multi-wavelength observations of FRBs, catching the same burst in radio waves, X-rays, gamma rays, and ideally optical light all at once, with high time resolution. Such observations can distinguish between models because different mechanisms predict different time delays and intensity ratios between wavelengths. The 2020 burst from SGR 1935 plus 2154, the galactic magnetar FRB, gave a tantalizing glimpse of this. The radio burst and the X-ray burst were associated, but with a small time delay and a very specific ratio of radio to X-ray energy. Both of these are model-dependent predictions, and they ruled out some models while constraining others. But one event is not enough. Astronomers need to catch more galactic FRBs, or more extragalactic ones at high signal-to-noise ratio, with all their telescopes simultaneously. There is also a purely observational puzzle that has deepened the mystery of emission mechanisms. Some FRBs show highly organized, complex subburst structure that looks almost too ordered to be random. One repeating source, studied in detail by multiple groups, showed a series of subbursts separated by strikingly regular intervals, almost as if a clock was ticking inside the burst itself, with each tick producing a pulse of radio emission. These quasi-periodic microstructures, as they're called, could reflect the rotation period of the magnetar, or oscillations in the magnetospheric plasma, or something else entirely. They are among the most detailed features in FRB data, and they are among the hardest to explain. Every time a new analysis reveals a new layer of structure in FRB data, the theoretical picture becomes more complicated, And every time the theoretical picture becomes more complicated, the appetite for more and better observations grows more intense. It is a cycle of discovery and confusion that defines the frontier of astrophysics. Chapter 11. The Localization Breakthrough, Connecting FRBs to the Cosmic Web. We talked earlier about how FRBs can be used to probe the intergalactic medium and solve the missing baryon problem. But to use FRBs as precision cosmological probes, you need precise positions. You need to know exactly which galaxy an FRB came from, at what distance, along what path through the cosmos. For most of FRB history, this was impossibly hard. The large beams of radio telescopes, the broad patches of sky they resolve as a single point, made precise localization nearly impossible. You might know that an FRB came from a particular square degree of sky, but that square degree might contain hundreds of galaxies, and you couldn't tell which one was the host. The breakthrough came from a combination of techniques: real-time detection, rapid multi-telescope follow-up, and increasingly sophisticated interferometric methods. Real-time detection was the first key. Early FRBs were detected from archival data, days or years after the event. By the time anyone knew the burst had happened, there was nothing left to follow up on, but as automated detection systems improved, telescopes could flag an FRB within seconds of detecting it, and issue alerts to a global network of observatories that could then immediately slew to the same patch of sky to look for any afterglow or counterpart. This was exactly the kind of rapid response system developed for gamma-ray bursts, adapted now for FRBs. But even faster follow-up didn't help much if the radio position wasn't precise enough. The real localization breakthrough came from interferometry, using multiple radio dishes separated by large distances to observe the same burst simultaneously and combine their data to achieve the angular resolution of a telescope, the size of the separation between the dishes. The Australian Square Kilometre Array Pathfinder, ASCAP, was particularly important here. ASCAP is an array of 36 dish antennas spread across a region of Western Australia, and unlike a single dish, an array can produce interferometric positions that are dramatically more precise. ASCAP started detecting and localizing FRBs with arc-second precision, good enough to identify a specific galaxy as the likely host, in 2019 and 2020, producing a series of landmark localizations. As of 2023, somewhere around 50 to 60 FRBs have been precisely localized to specific host galaxies. This is a small fraction of the total known FRB population, but it is enough to start drawing conclusions. What does the sensors of host galaxies tell us? First, FRBs do not come exclusively from any one type of galaxy. They come from massive spirals, from dwarf irregulars, from ellipticals, from galaxies undergoing mergers. They span an enormous range of star formation rates, stellar masses, and metallicities. This diversity is real, and is not going away as more hosts are identified. Second, FRBs are not preferentially located in the centres of their host galaxies. They don't seem to be associated with the central supermassive black holes in the way that some other exotic radio sources are. But they also don't strictly follow the distribution of star-forming regions within their hosts. Their spatial distribution within host galaxies is complex and varies from source to source. Third, and this is important for cosmology, the redshift distribution of localized FRBs spans an enormous range. Some hosts are nearby, just tens of millions of light-years away. Others are billions of light-years distant. This range is what makes FRBs such powerful probes of cosmic structure. They give you sightlines through the universe at many different distances and directions, each one sampling a different column of the intergalactic medium. In 2023, a team using the Craft survey with ASCAP, along with VLT optical follow-up, reported the detection of an FRB originating from a galaxy at a redshift of around 1, meaning the light travelled roughly 8 billion light-years to reach us. This is one of the most distant FRBs ever localized, and its dispersion measure, combined with its known distance, provides a beautiful direct measurement of the amount of matter the signal passed through in 8 billion years of cosmic travel. The plan, going forward, is to do this for thousands of FRBs. The Square Kilometre Array, SKA, the next generation of radio telescope infrastructure being built in South Africa and Australia, will detect FRBs at rates that make CHIME's current output look modest. With SKA, astronomers expect to detect and localize potentially millions of FRBs over its operational lifetime, building up a three-dimensional map of the universe's matter content that will answer fundamental questions about dark matter distribution, the large-scale structure of the cosmic web, and the history of cosmic magnetism. But we're getting ahead of ourselves. Let's come back to the present, and to a series of recent discoveries that have shaken the field in ways that nobody fully expected. Chapter 12: The Ultra-Long Period Objects, a new class of cosmic mystery. In early 2022, astronomers reported the detection of something strange coming from a source within the Milky Way, a radio signal repeating with a precise period of 18.18 minutes, not milliseconds, not seconds, minutes. Every 18 minutes, give or take a fraction of a second, a pulse of radio waves arrived at the Murchison Wide Field Array in Western Australia. Each pulse lasted between 30 and 60 seconds. This object, dubbed Gleam XJ, 162.759.5-523504.3, fit into no existing category of known radio sources. Pulsars rotate in milliseconds to seconds, certainly not in 18 minutes. Magnetars rotate in seconds. The slowest known rotating neutron stars at the time had periods of a few seconds at most. To have a neutron star rotating with an 18-minute period was, according to conventional models of neutron star spin-down, essentially impossible. Such a slow rotation should have caused the neutron star to cross what's known as the death line and stop producing radio emission entirely. Yet here it was, pulsing steadily for about 3 months of observations in early 2018 data, discovered in the archive, and then going silent. A few months later, another similar object was announced, GPMJ 1839-10, this one pulsing with a period of 21 minutes, and this time, when astronomers went back through archival data, they found it had been active for at least 35 years, a source rotating, if that's even what it's doing, once every 21 minutes, and apparently staying above the pulsar death line for decades. These ultra-long period objects, ULPs, as they've started to be called, may or may not be the same kind of object as FRB sources. Their pulses are generally longer in duration and less energetic than classic FRBs, though some of them do show FRB-like millisecond substructure within their broader pulse envelopes, but they represent a completely new regime of neutron star physics, or possibly a completely new type of object that nobody had considered before. Are ULPs exotic white dwarfs? White dwarfs are the other type of stellar remnant, less massive and less dense than neutron stars, and a slowly rotating white dwarf could in principle produce radio pulses. Could they be a class of magnetically active white dwarf? Some researchers think so. Others believe they must be neutron stars in some unusual physical state. Others wonder whether they could be the long-sought anti-magnetars, neutron stars whose magnetic field configuration is fundamentally different from the conventional magnetar geometry. Whatever ULPs are, their discovery raises an uncomfortable question. If there are entire classes of exotic radio-emitting compact objects that we didn't know existed until we searched for them specifically, what else are we missing? How many other exotic phenomena are hiding in the data from radio surveys, waiting to be noticed? The discovery of ULPs has reignited interest in long-period FRBs and in the general question of what the slowest rotating neutron stars can do. If an ultra-long-period object can produce radio pulses at one pulse per 18 to 21 minutes, can it produce bursts that look like FRBs during particularly energetic episodes? Could some FRBs be produced by ULPs having giant flares rather than by conventional magnetars? The data don't rule this out. The boundary between pulsars, magnetars, ULPs, and FRB sources is becoming increasingly blurry, and some astronomers now think these are not truly distinct classes of objects, but rather different manifestations of the same underlying class. Neutron stars with magnetic fields, in various stages of evolution, at various rotation rates, in various environments, and that with enough telescopes and enough sensitivity, we will discover a continuous spectrum of behavior connecting all of these phenomena. This view, the neutron star zoo interpretation, is not universally held, but it is gaining ground as the observational landscape becomes richer and more complex. Chapter 13: The Information Encoded in Every Burst. Let's take a moment to appreciate the sheer density of information contained in a single fast radio burst, because it's easy to talk about FRBs as mysterious events, and lose sight of the fact that every single detection is, in a very real sense, a tiny book, a compressed record of an entire journey through the cosmos. When a fast radio burst arrives at our telescopes, here is some of what we can read from its signal. The dispersion measure, the amount by which the signal is spread across frequencies, tells us about the total column of electrons between us and the source. As we've discussed, this encodes information about the intergalactic medium and the location of the source. The rotation measure, the amount by which the polarization angle of the signal has rotated during its journey, tells us about the magnetic fields the signal has passed through, weighted by the electron density. This is sensitive to magnetic fields in the Milky Way, in the intergalactic medium, and in the immediate environment of the source. Some FRBs, particularly repeaters, show rotation measures that change from burst to burst, suggesting that the environment immediately around the source is evolving over time, that the magnetic field structure near the FRB machine is dynamic and turbulent. Scattering, the broadening of the burst profile due to multipath propagation, where the radio waves take slightly different routes through turbulent plasma, tells us about the clumpiness and turbulence of the material between us and the source. FRBs that are more heavily scattered must have passed through more turbulent material, either in their host galaxy in the intergalactic medium or in the Milky Way. Polarization properties, whether the signal is linearly polarized, circularly polarized, or unpolarized, tell us about the emission mechanism and about Faraday rotation in the source environment. Some FRBs are nearly 100% linearly polarized, suggesting a highly ordered magnetic field at the emission site. Others show significant circular polarization, which is a much rarer property in natural radio sources and whose origin is still debated. FRB 2020124A, a particularly prolific repeating FRB, showed wildly varying polarization properties from burst to burst, including some bursts that were highly circularly polarized and others that were hardly polarized at all, suggesting a chaotic dynamic emission environment. The burst time-frequency structure, how the brightness varies across frequencies, and how it changes over the duration of the burst, encodes information about the emission mechanism, the source geometry, and the local environment. The sad trombone frequency drift seen in many repeaters, where successive subpulses appear at progressively lower frequencies, is one of the most characteristic and puzzling features in all of FRB science. Multiple competing explanations exist, but none is universally accepted. And finally, the burst energy and rate, how bright the burst is and how often they occur, tells us about the underlying energy reservoir being tapped and the physical process driving the bursts. Repeaters with high burst rates and broad energy distributions tell a different story than rare, ultra-energetic one-off events. When you add all of this together, you realize that a millisecond of data from an FRB is extraordinarily rich. Far from being simple blips on a chart, these signals are layered, complex, multi-dimensional records of astrophysical processes occurring across billions of light years. Extracting all of that information requires sophisticated data analysis, careful modeling, and the ability to separate what happened at the source from what happened during the journey, which is not always easy or unambiguous. This is why the field of FRB science has attracted not just radio astronomers, but theorists, cosmologists, plasma physicists, particle physicists, and data scientists. The problems it poses are at the intersection of all of these disciplines. An FRB is simultaneously an astrophysical puzzle, a cosmological probe, a laboratory for exotic plasma physics, and a data analysis challenge. It is, in every sense, one of the richest problems in modern astrophysics. Chapter 14. The closest FRBs, reading the signals in unprecedented detail. One of the most productive developments in FRB science in recent years has been the increasingly detailed study of FRBs in nearby galaxies, events close enough that we can detect them with much higher signal-to-noise ratio, resolve their structure in extraordinary detail, and in some cases complement the radio observations with detections at other wavelengths. We already talked about the galactic FRB from SGR 1935+2154, but beyond that, FRBs from the nearby galaxy M81, just 12 million light-years away, essentially our cosmic backyard, and from other nearby galaxies have provided invaluable detailed views of what FRBs look like up close. The M81 FRB, associated with that globular cluster we discussed, has been particularly informative. It is a repeating source, and its relatively small distance means that each burst arrives with far more photons than a burst from a billion light-years away. This allows astronomers to study the polarization properties, the time structure, and the spectral properties of individual bursts in exquisite detail. The rotation measure of this source has been measured with high precision, revealing information about the magnetic environment in the globular cluster, which is itself a fascinating environment for studying old neutron star physics. FRB 02020124A, another repeating source discovered in 2020 and located about 1.3 billion light-years away in a Milky Way-like spiral galaxy, became one of the most intensively studied FRBs ever after a campaign in 2021 detected thousands of bursts in a 54-day period. Chinese astronomers using the FAST telescope, the 500-meter aperture spherical radio telescope in Guizhou province, the world's largest single dish, detected over 1,863 bursts from this source in 54 days. This extraordinary dataset revealed the complex time-varying polarization properties I mentioned earlier, as well as evidence for a complex magnetized turbulent environment around the source. The source was eventually localized to a star-forming region of its host galaxy, consistent with a magnetar origin. But the variable rotation measure, changing significantly from burst to burst over timescales of minutes, was puzzling and suggested that the magnetar sits in or near an environment with a rapidly changing magnetic field. One intriguing possibility is a binary system, where the magnetar's companion contributes a dynamic magnetized wind that changes the observed rotation measure. FAST has been a game-changer for studying bright and nearby repeaters. Its enormous collecting area, 500 meters in diameter, makes it the most sensitive radio telescope in the world for detecting faint radio signals. For FRBs, this means that sources that might appear as a handful of bright bursts per month to CHIME reveal themselves as torrential fountains of activity when FAST stares at them. The level of detail available from FAST observations of active repeaters has been at times almost overwhelming, providing so much data that the main challenge is theoretical. The models struggle to keep up, and beyond FAST, the international community has organised a number of coordinated campaigns in which multiple telescopes on multiple continents observe the same FRB simultaneously. These multi-telescope campaigns allow real-time localization through very long baseline interferometry, simultaneous multi-band coverage, and the kind of redundant cross-checked data that is necessary for the most robust scientific conclusions. Organisations like the European VLBI network, the Very Long Baseline Array in the United States, and ad hoc coalitions assembled specifically for FRB science have participated in these campaigns. The results have been consistently surprising. Every time astronomers have looked at an FRB in greater detail, they have found new structure, new behaviour, new puzzles. The answer to the question, what is an FRB really, seems to recede slightly further with each generation of improved observations, not because the observations are failing, but because reality is richer than any of the initial models captured. Chapter 15. The Dark Horse. Theories. Beyond the magnetar model, before we get to the latest frontiers and what comes next, it's worth spending some time on the minority viewpoints. The theories that don't rely on magnetars, or that push the physics in directions that most of the community finds uncomfortable, but cannot entirely dismiss. The majority position in FRB science today is that most FRBs are produced by magnetars, with the 2020 detection of a galactic FRB from SGR 1935 plus 2154 serving as the strongest evidence. But most is not all, and there are researchers who argue that some fraction of FRBs, perhaps a small fraction, perhaps a larger one, comes from sources that are not magnetars. One of the more persistent alternative proposals involves collisions between compact objects. When two neutron stars spiral together and merge, or when a neutron star falls into a black hole, the result is a violent event that releases enormous amounts of energy across many wavelengths, including, theoretically, a burst of coherent radio emission just before the final merger. This merger model for non-repeating FRBs is appealing because it naturally explains why some FRBs never repeat. The source is destroyed in the process of creating the burst. Neutron star mergers are known to produce short gamma-ray bursts, and if they also produce FRBs, the two types of events might be associated. Some researchers have looked for FRBs temporally and spatially, coincident with known gamma-ray bursts, with so far only marginal or unconfirmed associations, but the search continues. Cosmic strings are another more exotic proposal. Cosmic strings are hypothetical one-dimensional topological defects, effectively infinitely thin, incredibly dense threads of energy that might have formed in the early universe during phase transitions as it cooled from the Big Bang. If cosmic strings exist, they can interact with each other, forming cusps and kinks that emit intense bursts of gravitational waves and, in some models, electromagnetic radiation, including radio waves. The timescales and energetics of cosmic string events could plausibly match what we observe in FRBs. But cosmic strings themselves are hypothetical and have never been directly detected, so this proposal remains entirely speculative. Primordial black holes, another hypothetical class of object, black holes that formed in the very early universe from density fluctuations rather than from stellar death, have also been invoked as possible FRB sources. As these objects evaporate via Hawking radiation, the final stages of evaporation could produce intense bursts of radiation across a broad spectrum. However, the specific prediction of radio emission from Hawking evaporation requires specific assumptions about the physics of black hole evaporation that are not universally accepted, and the model has significant challenges matching the observed properties of FRBs. And then there's the cosmic comb model, which involves a neutron star being swept by the magnetized wind from a companion star or a nearby active region. As the wind's magnetic field lines comb through the magnetosphere of the neutron star, they can trigger bursts of coherent radio emission. This model has some attractive features for explaining repeating FRBs in binary systems, particularly the periodic ones, and makes specific predictions about how burst properties should change over an orbital cycle. None of these alternatives has gathered the observational support that the magnetar model commands, but science is not a democracy, and the history of astrophysics is full of cases where the minority view turned out to be correct. The magnetar model may explain 90% of FRBs, but the 10% that don't fit might be the most interesting 10% of all, and they might be revealing physics that we don't yet have the framework to understand. Chapter 16, The Numbers Game. How many FRBs are really out there? There is a number that astronomers throw around in FRB discussions that tends to stop people cold when they really sit with it. The estimated all-sky rate of fast radio bursts, meaning the total number occurring across the entire observable universe at any given moment, is somewhere between 1,000 and 10,000 per day. Some estimates push even higher than that, depending on assumptions about the faint end of the FRB energy distribution. Let's break that down into something almost graspable. That is, conservatively, one fast radio burst somewhere in the observable universe every single minute, possibly one every few seconds, events each releasing more energy in a millisecond than our sun produces in days, happening constantly, in every direction, at every distance, filling the universe like an endless invisible fireworks display that we are only now beginning to have the instruments to detect. We currently detect a tiny, tiny fraction of this. CHIME, the world's most productive FRB detecting telescope, catches a few per day at most. ASCAP catches a handful per week. FAST, when staring at known repeaters, captures thousands from individual sources but doesn't survey the whole sky. The reason we miss so many is simple geometry and sensitivity. Our telescopes cover only a small fraction of the sky, and only the brightest FRBs, the ones at the near end of the distance distribution, or the ones that happen to be intrinsically very luminous, trigger our detection thresholds. But this enormous underlying rate has a profound implication for the future. When the square kilometre array comes fully online, with its thousands of antenna elements spread across South Africa and Australia, collectively equivalent to a dish hundreds of metres across, the FRB detection rate is expected to jump by orders of magnitude. Some projections suggest SKA could detect hundreds of FRBs per day. Over the course of its operational lifetime, the total number of detected FRBs could reach into the millions. Millions of FRBs, each one a probe of a different sightline through the universe. Each one encoding information about the plasma, the magnetic fields, the large-scale structure of the cosmos along its path. The cosmological implications of a database of millions of FRBs with known host galaxies and redshifts are simply staggering. Consider what you could do. You could map the magnetic field of the universe on the larger scales, using the rotation measures of millions of FRBs in different directions and at different distances. You could measure the distribution of matter in the cosmic web, not as a statistical inference, but as a direct pixel-by-pixel reconstruction. You could study the evolution of the intergalactic medium through cosmic time, comparing the dispersion properties of FRBs at different redshifts to trace how the density and distribution of intergalactic plasma has changed as the universe evolved. You could measure the expansion of the universe, the Hubble constant, using the dispersion-distance relationship of FRBs as an independent method that bypasses all the systematic uncertainties that plague current measurements based on supernovae and the cosmic microwave background. The Hubble tension, the persistent, frustrating disagreement between different measurements of how fast the universe is currently expanding, is one of the hottest problems in cosmology right now. Current methods give answers that disagree by about 10%, and the disagreement has stubbornly refused to go away even as the measurements have improved. Some cosmologists think it signals new physics, perhaps a new form of dark energy, or modifications to general relativity, or new particles in the early universe. Others think it's an unresolved systematic error in one or both methods. FRBs offer a completely independent approach to measuring the Hubble constant that avoids many of the systematic issues that affect other methods. It's not a perfect measurement. There are uncertainties in the FRB approach too, particularly in estimating the host galaxy contribution to the dispersion. But as the FRB sample grows, those uncertainties shrink. Millions of FRBs is not science fiction. It is a realistic projection for what SKA will deliver within the next decade, and the science that flows from that dataset will, if the projections are anywhere near correct, transform our understanding of cosmology in ways that are difficult to fully anticipate from where we currently sit. But even before SKA, the telescopes we have right now are producing results that keep surprising the field, and some of the most surprising recent results have pushed FRB science in directions that nobody saw coming. Chapter 17, FRB2, 0220912A and the Precision Era. Every detail matters. In late 2022, a fast radio burst designated FRB 202209112A became the subject of an intense international observation campaign that exemplified what modern FRB science looks like at its best. The source was a newly discovered repeater, sitting at a redshift of about 0.077, meaning its light travelled roughly 1 billion light-years to reach us, and it entered an exceptionally active phase, producing hundreds of bursts per day during a window of several weeks. Teams around the world trained every radio telescope they could at it. The FAST telescope captured thousands of individual bursts with extraordinary sensitivity. The Allen Telescope Array in California monitored it simultaneously. The Effelsberg telescope in Germany, the largest fully steerable radio dish in the world, added its data to the mix. European VLBI network stations provided high-resolution position measurements. The coverage was unprecedented. What emerged from this campaign was a portrait of FRB production in extraordinary detail. Individual bursts showed complex substructure, multiple peaks, frequency drifts, varying polarization angles across the burst profile. The total energy distribution of the burst followed a power law, meaning most bursts were faint and relatively rare strong ones, consistent with a process driven by something like magnetic field energy release, where small events are common and large events are rare. This power law distribution is seen in other self-organized critical systems in nature: earthquakes, solar flares, even forest fires. It suggests that the underlying process has no characteristic energy scale. It can produce events across a wide range, governed by the same basic physics at all scales. The burst rate varied dramatically. During the most active periods, bursts arrived almost continuously, overlapping with each other in time. During quieter periods, hours might pass between detections. There was no obvious periodicity within the active window. Bursts didn't arrive at regular intervals, but the overall active window itself appeared to have some kind of structure in time, with activity gradually ramping up and then declining. The polarization properties were relatively stable for this source, mostly linearly polarized with a rotation measure that stayed roughly constant, suggesting a relatively stable magnetic environment around the source, in contrast to the rapidly varying rotation measures seen in FRB 20201124A. Two repeaters, both active, both producing thousands of bursts but with apparently different environments. Both are magnetars, probably. But evidently magnetars can live in very different surroundings. This is the lesson that the precision era of FRB science keeps teaching. The diversity is real, it is physical, and it matters. The variations between sources are not noise to be averaged away. They are signals carrying information about the specific properties: age, magnetic field strength, companion star, local environment of each individual FRB machine. Extracting that information requires not just better telescopes but better analysis methods, and this is where the intersection of FRB science with machine learning and artificial intelligence has become increasingly important. The datasets from modern FRB campaigns are enormous. A fast campaign on an active repeater might produce terabytes of raw data in a single night, containing thousands of bursts, each with complex time-frequency structure. Human analysts cannot keep up. Automated algorithms, neural networks trained to recognize burst signatures, to measure subpulse separations, to classify polarization patterns, are becoming essential tools, and the feedback loop works in both directions. Machine learning doesn't just help process existing data, it helps identify patterns that human analysts might miss. Subtle correlations between burst properties, weak periodicity signals buried in noise, systematic trends in how burst energies evolve over an active period. These are the kinds of patterns that automated analysis can reveal, and that then feed back into theory as new constraints. The application of modern data science to the FRB problem is still in its early stages, but it is accelerating rapidly. Some of the most interesting recent results in the field have come not from new observations, but from reanalyses of existing datasets using improved algorithms. Old data, looked at with new eyes, keeps yielding new discoveries. Chapter 18: When FRBs Get Weird. Anomalies that defy explanation. Science progresses not just through confirming predictions, but through confronting the genuinely inexplicable. And FRB science has had its share of observations that don't fit neatly into any current model, data points that sit at the edge of the theoretical framework and refuse to be absorbed. Let me tell you about a few of these anomalies, because they represent the true frontier of the field. The first is what some researchers call the downdrifting problem. In repeating FRBs, successive subpulses very commonly appear at progressively lower frequencies as the burst progresses. This pattern, the sad trombone effect mentioned earlier, is so consistent and so widespread among repeaters that it has to be physically meaningful. It's telling you something fundamental about the emission mechanism or the geometry of the emission region. But no theory currently explains it in a fully satisfying way. Magnetospheric models can produce frequency drifts by invoking specific plasma physics. Particles streaming outward through the magnetosphere and emitting at progressively lower altitudes as they decelerate, for instance. But making the quantitative details work is hard, and the predicted drift rates don't always match what's observed. Some theorists have proposed that the drift is not intrinsic to the emission mechanism, but is instead an artifact of how the signal propagates through plasma near the source, a kind of local dispersion, distinct from the cosmological dispersion that stretches the signal over its billions of light-years journey. But again, the quantitative predictions are not fully convincing. The second anomaly is the apparently bimodal population. Despite the enormous heterogeneity among FRBs, statistical analyses of large samples have repeatedly found hints of two distinct populations: a brighter, shorter, narrower band population that tends not to repeat, and a slightly fainter, longer duration, wider band population that tends to repeat. This bimodality is not sharp and clean. There is a lot of overlap between the two groups, but it is statistically present, and it suggests that maybe, despite all the theoretical enthusiasm for a single unified magnetar model, there really are two distinct types of FRB sources. What they might be is unclear. Perhaps both are magnetars, but in different evolutionary states. Perhaps one population is magnetars and the other is neutron star mergers. Perhaps the distinction is real but reflects environment rather than source type. The third and perhaps most puzzling anomaly involves the host galaxy of FRB 20190520b, a repeating source localized to a dwarf galaxy about 3.7 billion light-years away. This source has a dispersion measure that is dramatically higher than expected given its known distance, higher by a factor of several than what the intergalactic medium contribution should be at that redshift. The excess must come from either the host galaxy or the immediate environment of the source. But the host galaxy, observed optically, doesn't look extraordinary enough to account for that much excess dispersion. The most likely explanation is that the FRB source is embedded in a dense, locally confined region of plasma. Perhaps a nebula, perhaps the wind from a companion star, perhaps the remnant of a past explosion, that contributes enormous amounts of dispersion on scales far smaller than the host galaxy. FRB 20190520b also shows an extremely high and highly variable rotation measure, consistent with a very turbulent magnetized local environment. This source, together with FRB 121102, the original repeater, which also showed high and variable rotation measures, suggests that some FRBs are embedded in extreme, dynamic, magnetically complex local environments. Perhaps these are very young magnetars, still surrounded by the nebula blown off in their birth supernova. Perhaps they are magnetars in binary systems, bathed in the magnetized wind of a companion. Either way, the local environment is not just a passive backdrop, it is actively shaping what we observe, adding dispersion and Faraday rotation, scattering the signal, and potentially even amplifying or modulating the burst through various plasma effects. The fourth anomaly is subtler but potentially profound. Some FRBs show evidence of being gravitationally lensed. Gravitational lensing occurs when a massive object, a galaxy cluster, or even a compact object like a black hole, sits between us and a distant source and bends the light, creating multiple images or a characteristic magnification pattern. For most astronomical sources, detecting gravitational lensing requires careful optical observations, but for FRBs, lensing can in principle be detected from the burst structure alone if the lensed copies of the burst arrive at slightly different times, appearing as repeated subpulses separated by a characteristic delay determined by the mass and geometry of the lens. There are now several candidate FRBs that show evidence of gravitational lensing, multiple subpulses with properties that are consistent with lensed copies, rather than intrinsic emission structure. If confirmed, these would open an entirely new use of FRBs as probes of mass distributions along the line of sight, sensitive to compact masses as small as individual stars or even free-floating black holes. An FRB passing through a galaxy could potentially be lensed by every substantial mass concentration it encounters: clusters, individual galaxies, molecular clouds, stellar mass black holes. And the pattern of lensed echoes encodes the mass distribution of everything in between. It is a technique of almost sci-fi level sophistication, and it might be feasible with the next generation of telescopes. Chapter 19. The Alien Question. Why we keep coming back to it. I mentioned earlier that a Harvard paper considered the alien hypothesis for FRBs. Let me spend more time on this, not because it's likely true, but because engaging with it honestly reveals something important about what makes FRBs so extraordinary and why the human mind keeps drifting there. The search for extraterrestrial intelligence, SETI, has been ongoing in various forms since the 1960s. For most of that time, scientists searched for narrow-band radio signals, laser pulses, or other signatures of deliberate, artificially produced communication. Fast radio bursts don't look like communication signals. They are broadband, spread across a wide range of frequencies in a way that no efficient communication system would be. If someone were trying to send a message across intergalactic distances, an FRB is about the least efficient way to do it. But communication is not the only thing a technologically advanced civilization might do with radio waves. The paper by Avi Loeb and Manasvi Lingam at Harvard, published in 2017, made a specific and much more interesting argument that FRBs could be the leakage radiation from an alien megastructure designed to accelerate spacecraft. The concept is based on a real idea in physics, a laser sail, or light sail, in which a spacecraft is accelerated by the pressure of a directed beam of electromagnetic radiation. Scale this up to the level required to accelerate an interstellar spacecraft to a significant fraction of the speed of light, and you need a beam of radio energy so powerful that, Viewed from another galaxy, its accidental leakage might look like a fast radio burst. The calculation is self-consistent. The required beam power, the timescale, the energy, all of them can be made to match. This is the part that surprised many people who expected the paper to be obviously absurd. But matching the numbers is not the same as being correct. The same calculation tells you that you'd need a transmitter the size of a planet, powered by the entire energy output of a star, to produce an FRB bright signal. Building such a structure would require a civilization operating at what physicists call a Type II Kardashev civilization level, one that harvests all the energy output of its star. And you would need millions of such civilizations all over the universe doing this simultaneously to account for the observed FRB rate. This is, to put it charitably, a very specific and very demanding set of assumptions. It's not impossible philosophically, but the principle of parsimony, the idea that among competing hypotheses, you prefer the one requiring fewer extraordinary assumptions, favours the magnetar model by a wide margin. Magnetars exist. We know they exist. We've seen one make an FRB. Explaining FRBs with magnetars requires no new assumptions at all. Still, the alien question is worth engaging with because it highlights something real. FRBs are so energetically extreme that they push beyond what we casually associate with natural processes. When we first encounter something this powerful and this strange, the human instinct is to reach for the most dramatic explanation. It took decades of accumulated evidence about pulsars before the first astronomer who detected one, Jocelyn Bell Burnell, let go of the nickname she had privately given the signal, LGM-1, for Little Green Men. The history of astronomy is littered with signals that looked artificial and turned out to be natural. Pulsars, quasars, the cosmic microwave background itself, discovered accidentally and initially mistaken for equipment noise. Nature, operating at its extremes, produces phenomena that strain the boundaries of the imagination. FRBs are the latest example of this. They are not aliens, but they are genuinely, verifiably as strange as anything aliens might plausibly do, and that in itself is a remarkable thing to be able to say about a natural phenomenon. Chapter 20. The Next Telescopes. What comes after? Chime and fast. The revolution in FRB science over the past decade has been driven almost entirely by new hardware. Chime transformed the field, fast deepened it, ASCAP changed what localization means, and the telescopes currently being built or planned promise to do it all again, at a scale that makes current capabilities look modest. The Square Kilometre Array is the headline instrument, spread across 2 continents, with low-frequency antennas in Western Australia and mid-frequency dishes in South Africa. The SKA will have a collecting area equivalent to a dish 1 square kilometre in size. It will be simultaneously the most sensitive radio telescope ever built, and one of the widest field of view instruments at its sensitivity level. For FRBs, this combination is ideal. SKA's low-frequency array, called SKA Low, will operate at frequencies below about 350 MHz, a regime where FRBs have barely been studied. Most current FRB observations occur at frequencies between 400 and 2000 MHz. Lower frequencies are harder to work with because they are more strongly affected by dispersion. The signal is spread out in time so much that individual bursts can become hard to identify, and because the Earth's ionosphere becomes increasingly problematic at low frequencies. But the rewards for pushing to lower frequencies are significant. At lower frequencies, the dispersive delay is larger, which actually improves the sensitivity to the electron content of the intergalactic medium. And some models predict that FRBs should be brighter at lower frequencies due to the spectral properties of the emission mechanism. SKA Mid, the dish array in South Africa, will cover frequencies from about 350 MHz up to several gigahertz. At these frequencies, localization precision is naturally higher and the confusion from ionospheric effects is lower. SKA Mid will be able to localize FRBs to sub-arc second positions in real time, meaning that within seconds of detecting a burst, the system will produce a position accurate enough to identify the host galaxy, trigger automated optical follow-up observations, and begin recording every wavelength of emission from the source. The real-time aspect is crucial. One of the persistent frustrations of FRB science is that most of what we know comes from the radio burst itself. We rarely catch anything else. Optical counterparts to FRBs have been searched for extensively and found in, essentially no cases, partly because the bursts are so brief that by the time a telescope can respond to an alert and point to the right location, the event is over. If an optical flash accompanies the radio burst, as some models predict, it would be visible only for milliseconds to seconds, requiring either an automated fast response system or a lucky coincidence where an optical telescope happened to be pointing at the right spot. With SKA's real-time detection and localization pipeline, paired with next-generation optical facilities, the Vera C. Rubin Observatory, the extremely large telescope, the chances of catching multi-wavelength counterparts to FRBs increase dramatically. This multi-wavelength synergy is one of the most eagerly anticipated aspects of the coming era in astronomy. Beyond SKA, several dedicated FRB instruments are being developed. The Canadian Hydrogen Observatory and Radio Transient Detector, CHORD, is the planned successor to CHIME, with several times greater sensitivity and significantly improved localization capability. The DSA 2000 Deep Synoptic Array, planned for construction in Nevada, will consist of 2,000 individual dishes spread across a large baseline, providing simultaneous wide-field imaging and sub-arc second localization for essentially every detected FRB. The Hydrogen Intensity and Real-Time Analysis Experiment, HIRAX, being built in South Africa, will complement the SKA by covering the southern sky in a frequency range optimized for FRB detection. And in the longer term, there are proposals for even more ambitious instruments, arrays in space, free from the limitations of Earth's ionosphere, arrays on the far side of the Moon, shielded from Earth's radio frequency interference, giant low-frequency arrays that could access the meter-wave regime where FRBs have never been studied. The picture that emerges is of a field on the cusp of a transformation. In the early 2020s, we know of a few thousand FRBs. In the early 2030s, we may know of millions. The shift in scale will be as profound as the shift that occurred in particle physics when the Large Hadron Collider came online. A step-changing capability that enables a new class of science. Chapter 21. The Theoretical Frontiers to What We Still Don't Know. Let's be honest about where we are. After 15 years of intense study, after thousands of detections, after brilliant campaigns with the world's best telescopes, after landmark papers in Nature and Science, after hundreds of theoretical models, we still don't have a complete universally accepted theory of fast radio bursts. We know that at least some FRBs are produced by magnetars. The 2020 galactic event confirmed that beyond reasonable doubt. But we don't know exactly how magnetars produce FRBs. The specific emission mechanism remains contested. We don't know whether all FRBs are produced by magnetars or whether some come from different sources. We don't know why some FRBs repeat and others don't, or rather we don't know whether all FRBs repeat at some level, with non-repeaters simply being sources we haven't watched long enough, or whether repeaters and non-repeaters are genuinely physically distinct classes. We don't know what determines the periodicity of periodic FRBs, whether it's orbital motion, free precession, or something else. We don't know why the FRB rate appears to be so high, thousands per day across the observable universe, and whether this is consistent with the known density of magnetars, or whether it implies a higher FRB production rate per magnetar than models predict. We don't know why some repeating FRBs are active for months and then go quiet for years, and whether this reflects something about the magnetar's internal evolution, its external environment, or the geometry of its emission beam. We don't know at the emission physics level how the coherent radio emission is actually generated, which specific plasma process is converting magnetic energy into directed, polarized, coherent radio waves with such extraordinary efficiency. We don't know whether the sad trombone frequency drift is intrinsic to the emission or is a propagation effect. We don't know whether the circular polarization seen in some FRBs is produced at the source or acquired during propagation. We don't know what the persistent compact radio sources associated with some repeating FRBs are, nebulae, accretion systems, or something else. We don't know what the ultra-long period objects are, or whether they are related to FRBs. We don't know whether FRBs are associated with gravitational wave events. The question has been searched, but the samples are still small. We don't know whether any FRBs are associated with neutrino emission, or whether the ultra-high energy cosmic rays that arrive at Earth from extragalactic space might be connected in some way to FRB sources. These are not small questions. Many of them are among the most fundamental in high-energy astrophysics. The fact that we don't know the answers is not a sign of failure. It is a sign of just how new and how rich this field is. FRB science is 15 years old. Pulsar science has been going on for nearly 60 years and still generates major discoveries every year. Gravitational wave astronomy, only begun in earnest in 2015, has already transformed our understanding of stellar evolution and cosmology, but still has enormous unknowns. FRB science is at the beginning of its mature phase. The instrumentation is catching up with the ambition. The theoretical framework is being built, challenged, revised, and rebuilt in real time. The community of researchers dedicated to the field has grown from a handful of specialists to hundreds of active scientists around the world. The output of the field, papers, data releases, new detections, is growing exponentially. And every week, somewhere in the world, a telescope is detecting a signal that began its journey hundreds of millions or billions of years ago. A flash of radio energy so powerful it outshines entire galaxies, compressed into a fraction of a second, carrying within it encrypted information about the universe through which it has travelled. And scientists are looking at that signal carefully, patiently, trying to read what it says. Chapter 22. The Bigger Picture. What FRBs teach us about the universe? I want to step back now and ask the biggest possible version of the question: why does any of this matter? Not in the narrow sense of why it matters to astrophysicists, that's obvious. But why does it matter in the broader sense to us, as inhabitants of this particular planet at this particular moment in cosmic history? The answer, I think, is that fast radio bursts are teaching us something profound about the nature of the universe we live in, not just about the specific objects that make them, or the specific gas they travel through, but about the deep character of the cosmos, about how extreme it gets, about how active it is, about how full of processes we didn't know existed it turns out to be. For most of human history, the night sky was the sky you could see with your eyes. Stars, planets, the Milky Way, the occasional bright comet. Beautiful, inspiring, but in a sense static. The universe of the naked eye is largely a universe of permanent things, stars that have been there for billions of years and will be there for billions more. The universe revealed by modern astronomy is something else entirely. It is a universe of extraordinary violence and constant change. Black holes tearing apart stars in streams of superheated gas. Neutron stars spinning thousands of times per second, locked in binary spirals that will end in cataclysmic mergers. Magnetars releasing in fractions of a second the energy output of suns. Galaxies colliding in slow-motion billion-year crashes. And now, fast radio bursts. Millisecond flashes of radio energy erupting from incomprehensible distances, flooding the universe with signals that contain the histories of everything between their sources and us. The universe is not a quiet, serene place. It is frantic and violent and endlessly active. And most of this activity is invisible to us without the right tools. Tools that humanity has only recently developed and is still developing. The radio window on the sky was opened less than a century ago. The FRB window specifically was opened less than 20 years ago. And in that short time, it has revealed a phenomenon that is simultaneously one of the most powerful and one of the most mysterious in all of astrophysics. This is what the history of science tells us, over and over again. Every time we build a new instrument, every time we open a new window on the universe, we find something we didn't expect. Pulsars were not expected, quasars were not expected, gamma-ray bursts were not expected, the cosmic microwave background was not expected, dark energy was not expected, FRBs were not expected, and each unexpected discovery has told us something fundamental about how the universe works. The pattern suggests something about what we don't yet know. If every new observational capability has revealed surprising new phenomena, then the capabilities we haven't yet built, the gravitational wave detectors of the future, the extremely large optical telescopes, the neutrino observatories, the space-based radio arrays, will almost certainly reveal phenomena we haven't yet imagined. The universe almost certainly contains types of objects, types of events, types of processes that we have no theoretical framework for because we haven't seen them yet. FRBs were unknown in 2006. What is unknown today that will be discovered in 2030? This is not idle speculation. It is the inductive lesson of the entire history of astronomy. The universe is bigger, stranger, more violent, and more surprising than any single generation of scientists has expected. FRBs are the latest reminder of this, but they will not be the last. Chapter 23. The Moment of Arrival. What it means to detect a signal. From billions of light years away. I want to close the scientific discussion with something that is easy to lose in all the technical detail, but is actually, to me, one of the most extraordinary things about FRBs. Let me try to describe what is actually happening when a fast radio burst is detected. Somewhere in the universe, let's say 3 billion light years away, something happens. A magnetoquake, perhaps. A sudden rearrangement of a magnetic field so powerful that atoms cannot exist in its vicinity. An event that releases more energy in a millisecond than our sun emits over weeks. A flash of radio waves propagates outward from this event at the speed of light, in all directions. For 3 billion years this signal travels. It crosses the galaxy in which it was born. It exits that galaxy and enters the intergalactic void. It passes through filaments of the cosmic web, threads of diffuse gas connecting galaxy clusters, and each electron it encounters slows the lower frequency parts of the signal very slightly, spreading it out across frequencies. It crosses galaxy clusters, bending slightly around their mass. It passes through the Milky Way's own halo, accumulating a little more dispersion. It enters the Milky Way's disk, and then, on a particular day and a particular moment in time, it intersects with planet Earth. It passes through our ionosphere. It hits an array of radio antennas in the Canadian wilderness. Electrical signals propagate along cables into signal processing computers. Within milliseconds, automated software recognizes the characteristic swept frequency pattern of a dispersed pulse. An alert goes out across a global network. In seconds, astronomers on multiple continents are looking at the data. The entire event, the event that triggered all of this, was over in less than 5 milliseconds. 3 billion years of travel and 5 milliseconds of detection. Every electron the signal encountered on its journey has left its mark in the shape of the detected pulse. The dispersion tells us how far it travelled. The rotation measure tells us about the magnetic fields it passed through. The scattering tells us about the turbulence in the plasma it crossed. And somewhere in the data, in the precise shape of the pulse, in the structure of its subcomponents, in the polarization of its electric field, is information about the event itself, about the magnetar, about the quake that shook it, about the environment it lives in, about what happened on that tiny city-sized ball of neutronium 3 billion years ago, when our solar system was barely formed, when the first single-celled organisms were beginning their slow revolution on Earth. A message from the past encoded in physics, travelling at the speed of light, arriving at an antenna in Canada, and being read by human beings who have spent their careers developing the tools to read it. This is what science is. This is what it does. It builds instruments sensitive enough to detect signals from incomprehensible distances. It develops mathematics subtle enough to decode what those signals say. It builds theories powerful enough to make sense of what it finds, and honest enough to acknowledge what it doesn't yet understand. And fast radio bursts, these brief, violent, beautiful millisecond signals from the far reaches of the universe, are one of the finest examples of what that process can achieve. And also, right now, one of its greatest ongoing challenges. Conclusion. The mystery continues. We started this story with an accident, a physicist, an archive, a signal nobody was looking for. And in the 17 years since that signal was found, fast radio bursts have grown from a single anomalous data point into one of the richest and most active frontiers in all of modern science. We know that they are real. We know that they are extragalactic, reaching us from distances of billions of light years. We know that they release energies so extreme that they outshine entire galaxies in the radio spectrum for milliseconds. We know that some of them repeat and some don't, and that the repeating ones show complex, rich behaviour that has occupied teams of scientists for years without being fully understood. We know that at least one of them, probably many of them, comes from magnetars, the most magnetically extreme objects in the known universe. We know that they can be used as probes of the universe's invisible structure, that they have solved the mystery of the missing baryons, and that they may one day resolve debates about the expansion rate of the cosmos. And we know that we don't know nearly enough. the emission mechanism remains contested. The diversity of host galaxies defies simple explanation. The periodic FRBs keep their clocks secret. The ultra-long period objects refuse to fit neatly into any existing category. The bimodal population hints at a deeper structure in the phenomenon that current theory hasn't yet articulated. What comes next is a flood of data. SKA, Chord DSA 2000. The next generation of radio facilities will detect FRBs by the thousands per day, by the millions per year. The theoretical frameworks that survive this flood will be the ones that are built on solid physics, that make specific testable predictions, that are humble enough to be revised in the face of contrary evidence. Science, at its best, is exactly this: a process of patient accumulation of evidence, of honest confrontation with what the evidence says, of willingness to discard beautiful theories when they don't match the data, and of genuine excitement in the face of genuine mystery. FRB science, right now, has all of these qualities. It is a young field, still in the explosive phase of discovery, where new observations regularly overturn what was thought to be established, where a single paper can reframe the entire theoretical landscape, where graduate students can make discoveries that no one has ever made before. The universe is telling us something. It is filling the cosmos with millisecond flashes of extraordinary energy from every direction at every moment. And we are slowly and painstakingly learning to listen. Somewhere out there, as you watch this video, a fast radio burst is travelling through the intergalactic medium. It has been travelling for hundreds of millions of years. It will reach us someday, or it won't, if it wasn't aimed our way. Either way, it doesn't know we exist. It doesn't care. It is simply physics, operating at scales and energies that dwarf anything in human experience. But we know it's out there, and we built the tools to find it, and that might be the most remarkable thing of all.